Let's think about finding the row space and column space of a matrix, or a basis for the row space and column space of a matrix. Well, we've seen that if we want to find a basis for the row space, we can do that by doing row operations. And if we want to find a basis for the column space, then we can do that by doing column operations. It's kind of unfortunate that we have to sort of do both, right? Because if we do row operations, that won't change the row space, but it will change the column space, which is really too bad. But let's find a basis for the row space and then think about the column space. So, right, essentially what we're going to do is reduce this to, do row operations to reduce this to a row echelon form. It doesn't even have to be reduced row echelon form. It can just be any row echelon form. So let's see, let's do row 3 plus row 1, and then while we're at it, let's do row 2 plus row 1. So we aren't changing row 1, so minus 2, 3, 0, minus 2, and then add row 1 and row 2, so 1, minus 2, minus 1, 2, and then add row 1 and row 3, so 0, 0, 0, 0. Okay. Well, I'd rather use this 1 in the second row to eliminate the 2 above it instead of using the 2 to eliminate the 1, just to avoid fractions. So let's switch row 1 and row 2. So 1, minus 2, minus 1, 2, 1, 3, 0, minus 2. Oh, I'm getting so sloppy that I'm going to make mistakes. Better clean this up. There we go. And then 0, 0, 0, 0 for row 3. And then we can do row 2 minus row 1. So that gives us 1, minus 2, minus 1, 2, and then 0, 4, 5, sorry, 1, minus 4. Okay. So, oh, and don't forget the last row. So this tells us, for one thing, that the row space is the span of, right, these row operations didn't change the span of the rows, so the original row space is the same thing as the span of these rows, but the first 2 rows are clearly a basis for that. So 1, minus 2, minus 1, 2, and 0, 5, 1, minus 4 gives us a basis for the span of the rows. All right. Now let's think about the column space of A. So we could do a whole other reduction using column operations to find a basis for the column space of A, but you know, that seems like a bunch of extra work. Wouldn't it be nice if we could use this row reduction that we did to find a basis for the column space? Well, to do that, what we would need to know is what columns here are redundant, right? The columns for this matrix span the column space by definition, so the question is, are they linearly independent or not? Well, suppose we had a linear dependence relation for the columns of A, like this. Now, we're going to think about this for this particular example, but actually this argument will work for any matrix, not just this particular matrix. So suppose we had a linear combination, suppose we had a linear dependence relation among these columns. Well, that tells us 2 things. So first of all, any coefficient that is non-zero, oh, I need a 4 here. Any coefficient that's non-zero means that I could solve this linear dependence relationship for that vector, and that displays that vector as a linear combination of the others, which means that vector is somehow redundant. We don't need it to get the appropriate span, and so we could eliminate that vector from our collection of vectors and still have the appropriate span, but also be closer to a linearly independent spanning set. Okay, but there's another thing that we can do when we have a linear dependence relationship like this. So remember, another way to think about matrix multiplication is that it's a linear combination of the columns of the matrix that you're multiplying by. So this linear combination on the left-hand side of this equation is really the matrix A times the vector of all the x's. And so the right-hand side is the 0 vector. Okay? Well, so, this linear, asking when we have a linear dependence relation is the same as asking what are the solutions to this equation. Well, how do we solve this kind of equation? We do row reduction, right? But what's the result of row reduction? Well, when we do row reduction, right, what we're really doing is multiplying on the left by elementary matrices, right? The elementary matrices are the matrices that realize row operations. Well, when we multiply on the left by the row operations that do this row reduction that we just did, that turns the matrix A into this matrix. Let's call this B. So now we have B times all our x's. But multiplying the zero vector on the left by those elementary matrices just gives you the 0 vector. Right? And remember, all of these elementary matrices, they're all invertibles. So this row reduction, we could go the opposite way if we felt like, for some reason. But now that so any solution to this first equation will also be a solution to the second equation with the matrix B, but that means that we have x1 times the first row of B plus, and so on, down to x4 times the last row of B. And again, that means so here we have a linear dependence relation among the columns of B. Now, the columns of B might span a different thing than the columns of A, but notice that if we started with a non-zero coefficient in our linear dependence relationship, the exact same coefficients show up down here in this linear dependence relationship, and so the same position will be non-zero. So if we could have expressed, say, the fourth vector in the fourth column as a linear combination of the others, then after the row reduction, we can again express the fourth column as a linear combination of the others. So if the fourth column was redundant before our row operation, it's still redundant after. So, but, just looking at this, how do you tell which is the redundant column, right? If we knew the third column was redundant, we would know that the third column in A was redundant and we could throw it out. But, how do we know? Well, there's a nice trick, because remember, in this kind of equation, because this matrix B is in reduced echelon form, we can tell very quickly for each row, we can tell very quickly which x values are non-zero, right? For this second row, this is telling us that 5x1 plus, 5x2 times x3 plus x4 equals 0, but because this is a reduced echelon form, or a row echelon form, we know that x4 is a free variable, so we can choose x4 to be 1, and that will demonstrate that there is a linear dependence relation where x4 is non-zero. So it's possible to make x4 non-zero in a linear dependence relation, and that means that this fourth column is redundant. But since it's redundant in our row echelon form, it's also redundant in our original form, so we don't need that one. Okay, but look, the third column is also corresponding to a free variable, And so by choosing x4 to be 0 and x3 to be 1, that demonstrates there's a linear dependence relationship where x3 is a non-zero variable. So that means that the third column here is redundant, and so the third column in the original matrix is also redundant. So really we only need these two. Right? There's no way to choose x4 is 0, x3 is 0, and also one of x1 and x2 non-zero. Right? If x4 and x3 are both 0, x1 and x2 both have to be 0 because they have pivots. Right? So we can't eliminate the first two columns, and that means that the first two columns span the So that means the first two columns span the column space. Span. So these columns were 2, minus 2, 3, 2, and 3, minus 5, minus 3. So we know just the first two columns span the column space, but we also know that they're linearly independent because there's no way to choose x1 and x2 to make these two columns to display. There's no non-trivial way to choose x1 and x2 to come up with a linear dependence relationship between the first two columns. So that means that the first two columns must be linearly independent in this row echelon form, but that means the original first two columns were linearly dependent in the original matrix. So that means these two columns are a spanning set and they're linearly independent, and so they're a basis. So the point of this whole thing is the following. By doing just a single row reduction, we can find a basis for the row space, and by choosing those columns that have pivots, we can also get a basis for the column space. So we can do those two things at once just by doing a row reduction. Right? We don't have to also do a column reduction. And so that's pretty nice. But in fact, it's even better than that, because if you notice, so the reason that there were two vectors here in the basis for our column space was because there were two pivots after we did our row reduction, right? But wait a second. The reason that there are two vectors in the basis for our row space, that's also because there were two pivot positions, right? So the number, what we've discovered here is that the number of vectors in the basis for the column space, so the dimension of the column space of A, that's the number of pivots, right? Which we also called the rank. But the dimension of the row space, right, that's the number of vectors in a basis, that's also the number of pivots, which again we called the rank. But that means that these two dimensions, these are equal. Not just in this example, but always. These are always equal because they're always both the number of pivots in a row echelon form. And that's really surprising that these two subspaces should have the same dimension, because remember, they aren't even subspaces of the same Euclidean space. The column space is a subset of Rm, or a subspace of Rm, and the row space is a subspace of Rn. So it's very surprising that these have the same dimension, but they do have the same dimension. And that lets us prove some really nice facts about column and row spaces. So on the one hand, the rank of a matrix is just the dimension of the row space. We noticed that already. And the dimension of a row space is the same as the dimension of the column space. That's what we just said. This also means that the rank of a matrix is equal to the rank of its transpose, which is very not obvious, not at all obvious. But this is true because the rank of A is the dimension of the row space of A, but that's the dimension of the column space of A, because that's what we just proved. But the dimension of the column space of A is the dimension of the row space of A transpose, because the columns of A are the rows of A transpose. But the dimension of the row space of A transpose is the rank of A transpose. So that proves that these things are equal. All right, another nice consequence of all of this is that for any matrix, the rank has to be less than or equal to the minimum of the number of rows and the number of columns. Well, the rank is the number of pivots, right? But, I mean, how much room is there for pivots? You can have at most you can have at most as many pivots as you have rows, because you can only have one pivot per row, right? So that means that the rank of a matrix has to be less than or equal to m. Also, every pivot, there can only be one pivot in each column, so that means that the rank, you can't have more pivots than you have columns, so rank has to be less than or equal to n, but that means the rank has to be less than or equal to the smaller of these two, which is what I mean by minimum here. All right, also, one more thing, if you have an n by n matrix, then it's invertible if and only if its rank is n. So if and only if, that means if it's invertible, then its rank is n, and if its rank is n, then it's invertible. So how could we choose this? How could we prove this? Well, we already know that an n by n matrix is invertible if and only if A row reduces to the identity, right? But A row reduces to the identity if and only if its rank is n. So, we're done. All right. Also, right, there's more we can do here. If we have invertible matrices B and C, then for any matrix A, whenever these products are defined, all of these things have the same rank. So suppose we were computing the rank of A by doing a row reduction, right? So after a row reduction, you'd end up with some reduced echelon form, or reduced row echelon form. So this amounts to doing a bunch of row operations, which really are a bunch of elementary matrices. So if you multiply A on the left by a bunch of elementary matrices, you get to a reduced echelon form. Let's call the product of all of those elementary matrices E. Okay, well now imagine doing a row reduction for B times A. So we can, because B is invertible, we're assuming B is invertible, B is rank n, but that means that there are a bunch of row operations that will reduce B to the identity matrix. So if we multiply this on the left by a bunch of elementary matrices, we reduce B to the identity. So now we have I times A. So this is, right, I can't call it E because I've used that name. Let me call it F, I guess. Right, so F is the product of all of the elementary matrices that reduce B to the identity. But now, right, the identity times A, that's just A. So now if I multiply on the left by E, I get to the, right, I have E times A again, which is the reduced echelon form of A. But this shows that the rank of B times A is the same as the rank of this reduced row echelon form, which is the same as the rank of A. So, right, these are equal. Now, let's think about A times C. So we haven't worked too much with column operations, but right, column operations work very similarly. So if you can multiply on the right by elementary matrices to do column operations. So again, there's some big product of column operations that will get you a column echelon form, right? And because the rank of A is equal to the rank, because the rank of A is equal to the dimension of the column space of A, the number of pivots in the column echelon form will be the same as the number of pivots in the row echelon form, right? So this is still, the number of pivots here is still the rank of A. Okay, well, imagine C is invertible. We can, again, do a bunch of, multiply on the right by a bunch of elementary matrices that reduce C to the identity. And again, this is possible because we know that a matrix is invertible if and only if you can row reduce it, or equivalently column reduce it to the identity. But now, A times I is A, and then we can multiply by all of our column operations to get us our column echelon form. And so again, we see that the number of pivots after column reducing A times C is the number of pivots after reducing just A on its own, but the number of pivots in the column echelon form, as we've seen, is the same as the number of pivots in the row echelon form, and so that's the same as the rank of A. So all these things, right, all these three different ranks are the same, which is not obvious at all because we're multiplying by different matrices. In fact, B and C usually will be different sizes because A, for this last thing here, we didn't assume that A is square, so A might be m by n, in which case B is going to be m by m, and C is going to be n by n, right? So it's not at all obvious that these ranks should be the same, but in fact they are all the same. So you can see thinking deeply about row space and column space gives us some pretty interesting and non-obvious results.